sure by ITAMP. But thanks for saying. So I will, in my lecture, talk a little bit about the specific problem of quantum many-body physics, which are quantum impurity problems, information on polarions. So where we look basically at a single impurity in the bath. If you think about the last lecture, it's a very tiny subsystem in a bigger system, which we'll be looking at. And so my group is actually located in Munich, in the city where the photographer somehow managed to get these mountains really big. They are not as big when you look out of the window, but you can still see them. So it's a nice place to be at. But anyway, let me get started. So as we already heard in the lecture by Imani, we want to address phenomena as physicists which take place on vastly different scales. Actually stole this image from Imani's page. That's actually his experiment, one part of the experiment. He only prepares the lasers.
Not the right image, right?
No, but actually the right image is rather close to... Oh, no, this is actually not Munich. No, this is just some random nuclear power plant. I would not even know if it's used for scientific purposes. But anyway, we want to address phenomena which take place on different temperature and energy scales, maybe reaching from nanotelling regime, what, let's say, Immanuel is doing. I will come to the photons in a second. To maybe the mega electron volt range. When we think about, for instance, nuclear physics, we might even go to tera electron volt if we talk about LHC physics, or cosmic rays are even then 3 orders of magnitude to the right. And room temperature, where we are somewhere in between. And this might be very intimidating because we have to understand all these phenomena taking place on these different scales with a very limited sets of tools which we have. In particular, as theorists, basically, computer, paper, and pencil, and I will try my iPad and see how this goes. Anyway, one beautiful thing is, which actually does help us though in understanding this phenomenon, is the concept of the universality. We also heard about that before that. Although systems may take place on these, or physics might take place on these different scales, they are still described with the same underlying low energy Hamiltonian which we can use. So it really doesn't matter how exactly the implementation is. In some sense, also what Terry showed, this beautiful Hamiltonian after the solution of the one-dimensional interacting Bose case, we have just this Hamiltonian with the values of k and u, and this Hamiltonian can describe so many different systems. It can be actually particles jumping on a ladder in a protein to actually progressive experiments. And it's just this one single Hamiltonian, you just have to know k and u, which is the challenge to do. All right, let me give you 2 examples. Bosons and condensation. Okay, this is very optimistic, but okay, we can actually create this in nanotelling regime. It was first done in experiments in the 95, and then we had exactly this picture actually already this morning by Jonathan, that it was about 10 years later that one managed to produce a condensate of excitons in 2 dimensions. Not 2 dimensions, because it's actually heterostructures of the semiconductors in the cavity. And it's actually condensation at temperatures about 10 orders of magnitude higher absolute temperatures. And let me give you a different example from the context of a nuclear physics. In the 70s, Vitaly Efimov was thinking about some resonances which were seen in the collisions or in the production of carbon-12 nuclear cores, and one was thinking maybe these carbon-12 nuclear cores were made up out of 3 alpha particles which one could put together. In this context, one was then thinking, so how can 3 particles bind? And Vitaly found very funny solutions in this 3-body problem. Namely, where 3 particles can bind together, although 2 particles would not bind. And this gave then the name to those states as Bohr-Main states. 3 rings, if you would take 1 ring out, the rest of this thing falls apart. And some people actually did not even believe really if the solution is correct. But it was finally not proven in these type of things but again on the optical table in 2006 by the group of Untitled in Innsbruck. This time, same Hamiltonian, but realized at, I don't know, many orders of magnitude lower temperatures. Alright, and in my talk I want to show you one specific example basically from many-body physics where we can again use this time cold atoms to realize a certain phenomenon, namely the formation of Fermi bourons, which was then also possible to realize in novel two-dimensional semiconductors. Where we can really use cold atoms to actually do a quantum simulation of phenomena in the lab. All right. With this, let me come to what I want to talk about. So I thought I do more blackboard talk. Of course, we have to see the blackboard to see that. Okay. So what I want to talk about is basically the so-called quantum impurity problem. Actually, can you see that? It's also in the back.
Yeah.
Great.
Richard, can it fill the screen? Can you make it into a full screen?
So the thing is, I think I can turn this around.
No problem. You.
It doesn't change too much. But then it becomes smaller somewhere again. You know, it's kind of invariant. Nah. You know, I actually prefer to do it this way if you allow me.
That's fine.
Anyway. All right. So the question is, so we want to consider a so-called quantum impurity problem, which is basically the question, let's suppose you have a single particle, and this single particle would have, in addition, a bath, some medium which it can interact with. And this bath might be filled by some stuff. And so the core of the lecture will be concerned then if to have this impurity, and we have a medium, and we will ask what can happen with the system, and well, the impurity here can basically look in its room in the closet and ask, today with which excitations of a medium do I want to dress myself today? And build a new particle which might look a little bit different, and maybe it takes some phonons or something, and actually builds up a new collective object which we will then call it a boron. So it's, instead of a particle, we call it now a Bosonic particle. And this is the basic idea which we want to talk about. So how can an impurity interact with a medium, and what does it lead to? Which type of new quasi-particle properties does this particle have in the end? And the question is, now, where can we find actually borons? And we will link those notes also later, then available. All right. And let me give you, you know it's afternoon and stuff. So I thought there's a wine actually over here, but there is not. So I wanted to give some more entertainment also. So let me give you an example of boron formation in the classical world. Some of you guys might have seen me giving some colloquium or something, so some people saw that already. Okay. So what I want to talk about is the question, let's suppose, and interrupt me at any point also about this one here. Well, here I'm leaving my area of expertise a little bit. But anyway, so let's suppose we are at the one day in the lake, and the water is actually evaporating from the lake, and there will be water vapor. We cannot see, however, water in the air because the surface tension is so high that water droplets just built by water itself would actually break away again and again when we get molecules, unless you are at the supersaturated densities. So how do we see water? And water, not vapor, but let's say clouds in the sky. Well, what we basically have to do is, you can build a little factory or have some dust in the air, and these little aerosol particles. They are really tiny. They are the impurities in the many-body environment of the water vapor. And what can of course happen is that these little dust particles interact with their environment. They dress themselves up with the water vapor, and they build a new, let's call it, somewhat a quasi-particle. Oh, Jesus. This is what happens with our battery theorists. But anyway. In this quasi-particle we call a raindrop, and it has of course modified properties. Instead of a very light mass, it has a bigger mass. It's called an effective mass. And as theorists, we do proper transport experiments. And how do we do transport experiments? We want to measure the effective mass. Well, we put a force on the particle whose properties we want to investigate. What can we use? Let's use gravity, which pulls this range droplet down. But there's a counteracting force of the air actually streaming up. The force down, this is g times the mass of the particle. So the mass must be large enough so that we can actually feel if we have a certain critical mass, and that's just when we feel rain on our head. So basically what we do is basic detection when there's rain of, let's call it quasi-particle formation in the classical world of bourons. And then the question is, can we actually use, so some of my battery is empty, can we use the impurities in this environment actually to detect some properties of the environment? Can we learn something? And one of the ideas, if I have a hot cup of coffee and I want to see if it's really hot or not, one way is to actually taste it and drink it, maybe burn myself. The other way is, let's maybe go to Beijing, where we have actually many dust particles in the air. And by having those, we should see actually water vapor coming out. Here it's really clean air, probably I only have, let's say, 800 dust particles, so I don't see the steam. It is actually hot. So I'm not try. So this is a typical thing that we use already here in the classical world impurities as a detector of a many-body environment. And we can even use it in real time to see actually the flow of water vapor going in certain directions here. So now you can say, okay, that's just words. Can we also see this experiment at some place on Earth where we don't have many aerosol particles and see this detection of a many-body environment? And one possibility is to go in the pack ice as long as it's still there. And actually a friend of mine, Maria Martin, she went on the Swedish icebreaker on the different, they didn't want to look for these classical polars, but anyway, they went with the Swedish icebreaker to the pack ice. And you know the pack ice is covering the whole sea, so there's not even salt particles coming out of the water. So there are really no aerosol particles with which you could build actually water droplets. And she took a little video, which I wanted to show, where they do this experiment of detection of classical polars in the classical world. Okay, so let me start this. So what you will see is a video where they want to see if they can somehow see steam coming out of a really hot coffee, actually it's tea in this case. And let me see, somehow the sound doesn't work. But okay, so let me just say what they are saying here. So it's only 10 particles typically in the pack ice per cubic centimeter, so really not many. And what they will do now is they try to actually show that there's no steam coming out of his mouth. This is of course not a very good experiment. It's just 37 Celsius degree, or is it 100 Fahrenheit? Something like that. But anyway, so they do a better experiment. They take a cup of tea and see if they can see the water vapor coming out of there. And you can see it maybe slightly, if they wouldn't shake that much. It's actually Earl Grey and not coffee in this case. And you cannot see much coming out. So that's also, okay, so what? That's a video, so maybe that's just cold water. And of course you don't see anything. But then the lucky thing is there's a smoker on board. And he has, of course, his lighter. And he doesn't know why he should put the lighter there first, but then he just puts the lighter there, and by putting these aerosol particles, you suddenly see the steam coming out of the system. So that's kind of an example where we can use impurities to detect really the physics of a many-body environment and the changes of the impurities. Here the whatever stuff is in the lighter. I don't know. Let me give us a last example before I really start with the physics. One can also use impurities to control a many-body environment. Famous example in this context is climate engineering. Most famous example maybe the G8 summit in St. Petersburg a while back, when Vladimir Putin ordered his fighter jets to actually put salt rockets into the sky so that it would rain. It did rain, but over St. Petersburg. So this is where one uses impurities to control a many-body environment. And now again, in this lecture though, I want to talk about quantum impurities and how a single impurity interacts with a bath of particles and how an impurity becomes a polaron. Okay, with this, let me give you a couple of examples of where we can find polarons. The most famous example is maybe a so-called lattice polaron, where we consider a single electron moving through a lattice in a solid, and the electron will actually displace the ionic cores in the metal, or if it can also be a polarization cloud, if it's let's say a semiconductor. It should be a semiconductor. And the question is then, for instance, one can describe the system basically as an electron interacting with a low energy degrees of freedom system, which are the phonons. And one can ask then, how is the normal dispersion relation of an electron p squared over 2 times the electron mass change due to the interactions with the medium, and the particle will require some effective mass, so an enhanced mass as our water droplets did. And this, of course, is a very important example, the interaction between the electrons and the phonons, because in the end, if you have 2 of those impurities, they might actually exchange the excitations in the medium, which actually lays in the foundation, for instance, of BCS theory of superconductivity, where you have actually attractive interactions mediated by the exchange of the phonons. Also important, here we are very close to 1D physics. If you have a large, let's say, almost one-dimensional protein, so actually if you have a helix of a DNA, that would be rather closer to that. We can ask how electrons can be transported. And an electron hops from side to side in this protein and actually starts shaking the environment. That's also an example of the polarons, more in the context of, let's say, more complex molecules. Second example, actually Fabian, I think we'll talk about this in his lecture, where we can think about, let's say, a Fermi-Hubbard model as a model of high-density superconductors, where we have a system at, where you have on every lattice side an electron, and then you can ask how a hole in the system can hop from side to side, and this can also take place in an interferromagnetic environment, where the hole hops from side to side and frustrates spins. And so we actually interact here with the low energy excitations with the magnons. And so we build then what is called magnetic polarons. And I think Fabian might actually talk about that on Thursday. A different example, so far I talked about impurities interacting with bosons. We can also have impurities in systems interacting with fermions, electrons. An example is happening, let's say, in the X-ray spectroscopy of metals. That's a famous example where many-body wave function with an impurity in the system, or with a quantum impurity, compared to the wave function without the impurity, has 0 overlap. That's an example of the total destruction of quasi-particles or polarons. And how can we understand what is going on in these type of experiments? Well, this is what Immanuel showed. We can calculate the band structure of such a material. We get a couple of bands, and then we can fill up these bands with electrons up to the Fermi surface. And if you would look into this in real space, the density would be flat of our fermions in this metal. And if you then shoot an X-ray onto the system and excite a core electron to an upper shell, what we will find is that the surrounding fermions here will suddenly see a positive charge which comes from this core hole and suddenly have to rearrange surrounding this ionic charge. And this will lead then to a new configuration of electrons which is completely orthogonal on the initial state. And this is a famous example of the Anderson orthogonality catastrophe. This leads then in the absorption, so when you ask a shoot in an X-ray with a certain frequency, it will lead to an absorption which has these typical edges and no nicely resolved delta peak. The absence of the delta peak, that's a signature of that there's just no overlap of the initial state without an impurity to the initial state, to the final state with an impurity. You can see this nicely in also actually experiments where you shine an X-ray on the sequence of different metals here, and you see these typical edges in the spectrum, which actually are an example of polar tracing. All right. With these examples, let me jump over this, to a classification we can do about those polons. Namely, it's a question with which environment do they interact. Do they interact with fermions or do they interact with the bosons? When impurities interact with the fermionic environment, we can call them fermiporons. When they interact with the bosonic environment, it's called them bosoporons. Of course, there can be also other types of differentiation, could be topological excitation and so on.
So we don't care what the polar itself is because it's just one, and we don't care about.
Oh, that's the excellent question. No, it will play a role. So his question is very good. So if you have just a single particle, it really doesn't matter which statistics the single particle has, because if I want to see that significance, I have to interchange it with a second particle to know its statistics. However, in the end, we might be interested in, like, say, the electrons detected with phonons to actually do the two electrons and see if they want to pair up. And then it actually very much matters, of course, as soon as they have two impurities, which statistics they have. For my talk, I will focus mostly on the single impurity, and then it doesn't matter.
Sorry, I'm not sure, maybe you will make it clearer after, but I'm not sure I understand the difference in the post-polar and the fermi-polar, because it's still a particle Hall excitations of the Fermi-C, which are essentially bosonic in nature.
So that's true. So the excitation with which you interact are bosonic excitation. That's true. But the question is actually how this came about in the literature is really to ask, so what are basically fundamental particles building up where it's also non-fundamental particles, because you could say the lattice of course also fundamentally it's ions. But the environment, yeah, it's a name which came up. If you have an impurity interact with the ideal Fermi gas, of course you will see that it's a particle excitation. Yeah, that's a technical point in the little semantics in the end. So basically we would say, if you have an impurity interacting with helium-3, which is fermions, we call it a fermiporon. If it's helium-4 and it's bosons, then we call it actually bosoporons. Although also there the excitations are particle excitations, which are bosonic in nature. That's right. So we will focus in this lecture as an example on fermiporons. All right. So let me switch over. All right. So that's it. You know, I'm actually new to doing these switches to this different. So what we will consider is a system which will be a single impurity which is immersed in gas ferments. And please interrupt me here at any point. So it will be some impurity in a Fermi gas. Now, actually, what are the key ingredients we need in the system? So we need a single impurity. And actually, how many of you are familiar, use second quantization on a regular basis? But probably most of you are familiar. Good. So the impurity will be described, I will call it, to be created by an operator XP, which can create it out of its vacuum. And if it's just a single particle, if you like more to work in first quantization, you would just call this the cat state of a particle at momentum P. Then let's say we want to work in continuum in this lecture, so that we can actually label a particle it's actually by the momentum k. This might be in the periodic box, for instance, some which gives me the quantization of momentum. And let's say the impurity, just for the sake, since I'm using operators, I have to say now, coming back to your question, which commutation relations I want to use. Let's now, for the sake, since I will consider later semiconductors where these become excitons, let me use bosonic commutation relations for those particles. What else do we need? Well, we need the medium here, and the medium will be a Fermi gas created by fermions with operator Ck, and the Fermi C is built up, of course, by filling up all fermions up to the Fermi surface. And this will be Ck dagger acting on their vacuum state, and this will be just building what I call it here the Fermi C state cat. All right. Then we have to define our Hamiltonian, and this is very similar to actually what T.J.D. had in his talk. It will not be just bosons, we have now two types of particles. So let's take the fermions. They have a kinetic energy, Cp dagger Cp, and the impurity has a different dispersion relation, let's say xp dagger xp, and we have the interactions between particles, which is, and let's do 3D for now, just to choose a dimension. And I will not put vectors on all R operators, that is too much. And we have them interacting with the impurity. So here we have a typical density interaction measure where are our fermions, where are our impurities, and they interact with these. This potential, and the potential might be contact potential, which was already mentioned by here, and here we might put some constant u. And this we can Fourier transform this part here into momentum space. If we have a delta function potential, how would it look like in momentum space if I take the Fourier transform? Well, you know all of you know probably. It will be, of course, completely momentum independent, and so you get a term which looks like k prime q, and then we have c, ck, and x, k prime minus q, x k prime, dagger times u. And this is the interaction. All right. And so with this Hamiltonian we will work and actually ask now how can we solve this type of Hamiltonian. And this let me actually show you this new slide again. So this is our Hamiltonian we want to solve. The impurity fermions, and they interact with a interaction of Q, which is a constant in our case. And let's suppose we want to solve this Hamiltonian in absence of interactions. The solution of that problem is super simple. It's just a product state of an impurity, it's a momentum P, and the fermions are in their ground state, it's work at T = 0. And well, that's the whole story. In momentum space, I can depict it as a Fermi C and a single particle momentum P. Of course, I can take the Fourier transform of this object to real space and will correspond to an impurity in the background of constant densities. That's it. Now we can do something very simple, switch on interactions and do kind of almost like a perturbative expansion in the variation wave function. So the next term we could write is the following. Let's take again the Fermi C, but now let's take one single fermion at momentum Q, which will always be lower than the Fermi momentum, and kill it in the Fermi C. Then there's a hole in the Fermi C, and we will come to the answer to Kia's question. This fermion you have to put somewhere, so let's put it at momentum K, which is over here. But then the total momentum of the wave function must be P, its translation invariant system, must be conserved. So the impurity has to go to some momentum P minus the momentum K plus the momentum Q it just absorbed it. Now we can then optimize this variation parameter, which we will do in a second, and then ask how, after Fourier transform, the density looks like surrounding the impurity. And this whole collective object we call the Fermi boson. This is the dressed particle, which is then basically in the tangled state here between the impurity and the environment. This is what we called here before particle hole excitation in the system. And this Fermi boson has an energy quasi-particle weight Z and an effective mass. The quasi-particle weight Z is this prefactor here, and it measures how similar is actually the total boson wave function to its original non-interacting state. I was mentioning this orthogonality catastrophe before. There's something really, let's say, catastrophic happens, that you have to go on here with these particle hole excitations to infinity, and these terms then eat up all the quasi-particle weight in here, and the state is completely orthogonal on its original state. In terms of Thierry's lecture, if you do diagrams, which is not the best way of doing it, which is very much like expanding the series, you have to work really hard. I mean, you have to keep track of all diagrams, calculate them, or all terms in the series, and it's really nasty. Then you do this trick, and you are almost just done. So that's one of the examples of these beauties of these methods that Thierry is talking about. Let me also give you one historic side remark. This wave function was used a lot in the paper in the context of quadratrons by Frédéric Chély in 2006. It's one of these examples where in the Russian literature you can actually find it in 2012. This is the earliest I could find, but there might be more. And there's just a difference in citations. So this paper got 257 citations, and unfortunately Suris only got 9 so far. But I just want to mention this for the afterword, basically. So one should, because this is often called the Chély ansatz, or one should actually call it the Suris Chély ansatz. Right. So the thing is, if you want to understand how exactly we can calculate these properties, I didn't talk about really this interaction term. And so far in the lectures, we didn't talk too much about how we can understand this interaction. Let me just give you a very brief reminder. What does this U actually really mean? So far we only said, it's the scattering length, and let me explain this in actually very shortly, within 5 minutes or so. So what this U describes is the interactions between two particles. So we can ask about, at a certain distance r between two particles, what is the potential? And of course in quadratrons you have kind of like a Lennard-Jones potentials. And okay, we do not want to work too much with those Lennard-Jones potentials, so let's actually simplify this problem. And instead let's work with, let's say, square wave potential. If there is no square wave potential there, let's suppose, let's call this depth of the square wave u. If u would be 0, then the solution of the problem would just be a very simple scattering wave function, which is basically just a free wave function, which would be a sine wave k times r. So what happens if we switch on the potential here? What will happen is actually particles like an attractive potential, and they would of course like to go into the potential. So we can ask, what is the new scattering wave function looking like? Well, it will be drawn into the potential, and then outside of the potential there is obviously no potential, so the wave function must be looking exactly the same as the free one, but it will be shifted a little bit. And this little shift, this is called the phase shift, or this is actually given by the phase shift divided by the momentum of the particle scattering of the potential. And what basically the phase shift is telling us, so at a low momentum we can expand this in terms of momentum and the so-called scattering length. So this is supposed to be k, I'm sorry. This is k times the so-called scattering length. And what is important to note, this little phase shift is the whole widthness of interactions in the system. So I can look at the wave function at very large distances from the potential. From the little phase shift, I can extract how is actually the potential looking like. And it can actually at low energies parameterize it by a single parameter. And that is the scattering length. And it's really just this witness. You do not even have to know anything about the potential. Just ask the wave function. It will tell you not about how the potential exactly look like, but what are the consequences of the potential. And this is the scattering length which we actually talked a little bit about before. So what one wants now typically doing, one wants to use, as I said, contact interactions here. So we will make this potential deeper and actually more narrow by keeping the phase shift, which is this guy here, just the same. And so we will pull this down, make it actually more narrow in this extent. Let's call this 1 over a momentum scale lambda, and this is called the UV cutoff. And one can ask now is, how is U related to the scattering length for actually such a model? And we know from the Lippmann-Schwinger equation, so I will not repeat now complete actual scattering theory. So from the Lippmann-Schwinger equation, we learn that 1 over U is, I actually forget now about the prefactors, is given by 1 over scattering length times the UV cutoff, you know what. Let's put wrong equations there. So it's the reduced mass divided by 2 pi input h bar squared, 1 over scattering length, minus reduced mass divided by pi squared, and here comes UV cutoff. So now we learn how actually the scattering length is connected to U. And basically we can plot this. Let's put here U, and what scattering do we get out? At U equals 0 we have no scattering length. If we make the U larger, we can actually invert this equation. So we will get, let's see, so we have something like scattering length, I'm putting this on the other side, is approximately proportional to 1 over 1 over U plus a lambda. So if U is tiny, this is infinity, this is 0. If U becomes larger and is a negative, we will still have a negative quantity here, which becomes more and more negative. At some point, 1 over U plus the UV cutoff, this is big lambda, this will become actually 0, we have divergency, and the scattering length comes back from infinity. And this is actually the point where the potential does something special, namely at this point, the potential will be so deep that it supports a bound state, and the wave function here will be bended so much that it becomes a bound state, a wave function, and we have a bound state in the system, and then the scattering length becomes positive. Alright, so what we learned is we can parameterize U by the scattering length. If the scattering length is positive, we have a bound state in the problem. This will be important for the nature of our problems, which we want to discuss. Alright, so now what we want to talk about is now, so how can we solve actually this problem with this wave function? And this is basic variation wave function that we choose. We have parameters alpha, p, and some alpha which depends on k and q. K is the momentum to which we put the Fermi, and q is where the particle came from. So I want to show you now how very quickly one can do a calculation done about 8 years ago to explain experiments in cold atoms, and which is now also one how one can explain the absorption properties of two-dimensional semiconductors. And so basically this I will now do in the rest of this lecture and also tomorrow, and then show how one can actually use it really to see how one can describe these experiments in these different realms. And it's really a simple calculation. I just want to show it to you to have trust that it just take a couple of days and you can do these calculations very easily. And there are still a lot of things which are not studied yet in these systems. So you can extend them also to two impurities and so on. And there are a lot of open questions. So it should be kind of like a possibility if you're interested in these things to have a start at this thing. So we want to do variation principle. So what we have to do is we have to minimize the energy of the system. Maybe it's a little bit too slow. You're looking like maybe it's a little too slow, so I will actually skip ahead a little bit here. So what we minimize is the energy expectation value, very important, divided by the norm, because the state is not necessarily normalized. So what we want to do is we want to minimize this object, df, over the variation parameters, let's call them psi, of the system. And what we will, and we have to put this whole thing to 0. And this is equivalent, as we can show, to actually minimize I call it L, it's not exactly the Lagrangian, but we want to minimize this object here, h minus the energy of the system times psi, where E is defined in the end as whatever comes out as the energy expectation value of the system. So this object we have to calculate. Alright. So let's actually do this very briefly. So it's maybe a little bit too technical lecture now for the after dinner talk in some sense, but apologies for that. Let's actually do the calculation of this Lagrangian. Alright, so we have our Hamiltonian in the system, which is luckily here still in the back. So we have here this Lagrangian, this Hamiltonian, which we want to actually calculate the expectation value of that state of. So we have to sandwich this state on both sides of the Hamiltonian. Let's only do it for one term, the very simple one here, where we take the expectation value with respect to the kinetic energy of the impurity. And if we do this, okay, we have to sandwich our system. Our wave function has two terms, expectation value of this, and we have this second term here. So let's actually do this. We have psi h, the kinetic energy part of the impurity, which had now two contributions from the first term here. This can be sandwiched from the right side and from the left side in the Hamiltonian here, and this will give us just the kinetic energy of the impurity. In the second term, let's make it a little bit more detailed. We have the interaction of the system, which has K prime and Q. Sorry, here I'm doing interaction. And then we have the kinetic energy. So I take now this state here. We have now the Fermi, which is this term, times the vacuum of the impurity. Let's do this actually first. The impurity is a momentum P plus Q minus K. Dagger is here, then you see Q, C, K, dagger, prime, and, oops, I'm sorry, these terms I go to the Fermi. And then we cheat a little bit. Let's just copy paste this. So we put this here and take our impurity, and it says momentum P plus Q minus K. And then we see, aha. Oops, vacuum. Excellent. We have. And of course there's the alpha, thank you very much. We have alpha P, K, Q, prime, star, alpha, K, Q, P, and no star. Alright, so actually what we can see now is that we destroy one Fermi momentum Q, but then this momentum K is above the Fermi C, so that we have again overlap. We have to ensure this is actually wrong here. Sorry, I messed up. It's the Hermitian conjugate of our wave function here. This part here, CK, CQ dagger, CK prime without the dagger because of the Hermitian conjugate. We have to make sure that actually we get out the same state again, so that we actually do have overlap, and therefore K prime has to be equal to K and Q prime has to be equal to Q. But on the other hand then, this Q is equal to this guy and this is equal to that guy, and thereby we actually get out in the end that and overall you can evaluate this thing and we will get an expression omega. Oops. This is the kinetic energy, the sum over kinetic energy, KQ, KQ prime. We get out P plus Q minus K and alpha KQ. Oh, I'm sorry. That is true. You see? All right. And so we can actually calculate the kinetic energy of the whole system, which is then in the end omega p times alpha p absolute value squared plus this object here, and this is our kinetic energy. And now we can keep on doing this with every term, and since it's only 5 minutes left, so one can actually calculate the complete object, but you see it's just 3 pages. And what we will get is in the end a rather simple expression for the total Lagrangian. So Vernon has actually the parts which come from just the bare part of the impurity. It's of course just given by the kinetic energy of the impurity without the environment. Then it's also related to the total energy of the Fermi sea, which has nothing to do with interactions. And then there is the question, how much energy is sitting in these particle-hole excitations which we created in the wave function. And this is given by, okay, how much energy is in the particle excitation above the Fermi surface? It's epsilon k, k squared over pm. But then we took out the fermionic momentum q in the system, which costs us energy, or which is actually not needed. This is epsilon q and with a minus sign. And then we have an impurity which we had put into some momentum state p plus q minus k, and thereby we have here the kinetic energy of the impurity. Like this one can go through this object where one can see that interactions can take one out of the state, where interactions can take us out of the state, where interactions take us out of the state P and bring the impurity into a new momentum and into that state, and thereby we get cross terms. And these cross terms are just those terms here. And now what we do is we actually minimize this object L with respect to the variation parameters, which are I'm sorry, this is getting too low. So now we actually minimize dl over the variation parameters, which are alpha p star, and set it to 0. And we do the same with respect to the alpha kq p star. We put this to 0. But that's rather simple. If you look at this expression, if you take the derivative with respect to alpha star, we get a term from here. Let's see, a term from here, one term from here, and that's it. So it's actually rather simple to take the derivative, and if you do this in the end, you will get this rather simple expression which you can actually see here. Where we get just 2 terms. So if you take the derivative with respect to this parameter alpha p, we get this part here from the kinetic energy which we had here. So I actually have set now EF to 0, so it's just omega p minus the energy. This is the term here. And then you get this term which comes just from this cross term in the interactions, which was this term, alpha p star derivative just gives me this part over here. And like this, you just carry on, and you can also take the derivative with respect to alpha p star, I mean this alpha kq star, and you get the same equation. It's rather simple equations, and what you see is actually a linear equation system. In principle, you can solve this also already on the computer, but you can solve it analytically, and this is what one can do so nicely in this problem. Since this, however, that is probably a good trying to stop since it's so. Or actually, when did we? So Hussein? No, Hussein is not with us anymore. Excellent. In those 6 minutes, let me show. So one can actually solve this problem in a nice way by doing the following. There's a little trick, and this trick will reappear in a lot of these problems also if you do Q of T. You will very often do this little trick. So we have this simple equation system for the parameters alpha p and alpha k q p. Now, there's one thing what we can do is, one can actually combine this portion here and this portion of our equations, and you write down some collective new variable for them, which is written in this form. Now, then what we can use is actually this equation here will now look like it's again this kinetic energy, but then it's u divided by v times exactly this object phi. But that means we can, so we have this equation plus u divided by v times chi, we can just solve for alpha kq by just taking minus u times v times chi divided by whatever is here on the left hand side. We write this object down. Alright, then what we can do is next we take this object and we can insert it then exactly in the definition of this chi. We insert this over here into this term here, and what we can do is then, well, here's then an object which is again proportional to chi of q, but that's not inside the summation. So we can pull it out and put it on the other side of the equation, and we get then chi of q is proportional to 1 minus whatever was here, modulo with this chi q, which we pulled out, and this must be equal to alpha p. But then we can invert it and write it in terms of alpha q. And then we are almost done already, and actually then insert this alpha kq and insert it down to the first equation. Because in the first equation, this is not quite this object here, but you can always put here a plus alpha p minus an alpha p. And if you do this, what we will find is just the first term, as we have it here, and then we have here plus alpha p, and here minus alpha p, and we only have to insert the additional sum over q, because this was a sum over kq. And then what we have here is this object, and this is just a sum over chi q, and this is, in this object here is actually, one has to be now remembering that the u which we had was related to the scattering length. And if you remember now the following, the scattering length was actually related to the scattering constant u. But if the UV cut of lambda goes to infinity, that means we go to contact interactions and make this potential very narrow. This means lambda is very large. At fixed scattering length, what does it mean for u if lambda becomes very large? It means that u becomes tiny, actually goes to 0, or it's just 0 minus. And that means in the end that a lot of terms which we just discussed actually will become actually very, or will, that actually many of these terms which we discussed will become actually small. In particular, this term over here will just go to 0 in the end, because it's this is just a number. This is the sum over all momenta below the Fermi surfaces, and the number of fermions times u is actually 0. So this term is gone, and we only have this term actually left to deal with. And so we have only this term to deal with. Let me show you to you again. Oops. This is actually a problem that is not fitting here. Alright, so we have this term left. Now let's see, this was this equation here. We have here the chi. We can now insert chi into this equation. Inserting chi into this equation, this is proportional to alpha p. This will be proportional to alpha p, and alpha p cancels. And what we solved is we have now an equation which just contains alpha p times something which only contains the energies of the particles, omega p, the dispersion relation of the fermions, and the interaction strength. And as long as alpha p, which is the Bosonic particle weight of the particle, is non-zero, what we will have is that this object must be zero. So the energy is solved, but it's such a simple analytical equation which gives us the energy of the impurity. And then by inserting the Lippmann-Schwinger equation, here we have rho to the -1, we can actually integrate this even analytically in the end, and we have a final expression of our Coulomb energy. And this is actually the basis to explain experiments which I will talk about next lecture, to explain the experiments by Martin Zwirlein, where he for the first time actually measured impurities in the Fermi gas. And finally, with this solution of this equation which we will discuss now in the next lecture, one can get within 1% of the result already for the energy of an impurity in the Fermi gas. And this interestingly also gives you then a precision of 1% if you compare to excitons, for instance, interacting with the electrons in transition metal dipole it's two-dimensional, the semiconductors, which we will also talk about actually tomorrow morning. And with this, it's 6 minutes past, so let me actually stop here. That's what I want to stop. Thank you.
Questions?
Can I ask a question? So if V is super small, probably the coefficient alpha, or how you call it, is just V. Because it would be the straightforward perturbation theory. So,
oh yeah, that's true. You mean if it's really small, it's
very
perturbation
small.
theory, absolutely. Then it's proportional, you could do actually perturbation theory.
yeah, then you just do perturbation
Right,
theory.
because then actually this prefactor Z, absolutely.
So is there a diagrammatic representation in terms of whatever self-consistent diagrams or something of the
That will be actually part of the lecture tomorrow also.
Richard, you can flip it.
Oh. That's nice. All right. So the question was basically, can you understand this whole problem about an impurity propagating in the system, and then the impurity can actually scatter in the fermions in the environment with some interaction. And what you can see here is we have a fermion which we take out of the Fermi sea at some momentum q, and it goes to some momentum k, which is above the Fermi surface, and the impurity comes in at some momentum p, and it finally goes to some momentum p. Okay, here it will be p plus q minus k, and then it can do this again, and you can do this again and again and again. So if you resum all these diagrams to infinite order, and then, that's now a technical point, close actually this loop here, you'll find that this is a so-called non-self-consistent T matrix summation. So this is how we actually treat this problem typically in Q of T. But it turns out that this full diagrammatic series expansion would look really complicated. And then it's just the calculation of the variation principle with this very simple wave function. But it's full diagrammatic resummation of non-self-consistent.
So this is showing the ladder.
That's a ladder resummation.
Can you also tell when the orthogonality capacity will occur from the expression for...
So from this expression which I have shown you, no, you will not be able to tell that. Where you will see, however, why it can occur is the following. If you look really closely what is happening here. So if you have an impurity which gets scattered from some momentum p to some different momentum, you can ask yourself how much energy does this cost you? And you will have some momentum transfer, let's call it delta q, which will go onto the impurity. Now this will cost you. And it will cost you this momentum transfer approximately it will make kinetic, so let's suppose the impurities at momentum p is 0. Then after the collision it will have actually the momentum q. Its kinetic energy will then be q squared over 2m, and you will have a problem. If the mass goes to infinity, there is no kinetic energy protection anymore. And thereby you can generate a lot of particle-hole excitations in the Fermi sea, because how much energy does this cost me? If I have one fermion and take it from here and put it here, we can ask ourselves how much energy does this cost? Then you can generate tons of those and you never have to pay. And thereby you generate more and more terms of this expansion, which will hurt you in the end. And which we in the end will really do this, what I was actually mentioning really briefly, where you generate more and more of those terms, and they are eating up all the Z over here, and in the end nothing is left. But you cannot see from the final expression which I have shown. You will go to the next order, and then you will wonder, damn it, when does this finally converge? And then one should probably use different methods of calculating this. And for instance, typical choice, very simple. If you look at Anderson's paper, it's just a calculation of the stated determinant. It's actually really simple.
So orthogonality study happens only in the limit of M or
No. Then there are these special systems of 1D where they even happen if the particles are mobile. But 1D in some sense is a little bit special there. It's also that you have a impurity in 1D chain. If it wants to move, it really has to hit those guys. And it's obvious we have seen even, if you want to diagnose this problem, the typical cues of freedom are those collective objects. So 1D is special, so that even happens for mobile impurities. And a problem which is still unanswered in some sense, or still debated, is in 2 dimensions. What happens to an impurity just an epsilon away from infinite mass? Is there a quasi-particle or not? And this is still debated, and there's no exact solution for this problem. I think you guys, for instance, I think TS, for instance, expanding this now to not only a one-dimensional strip, but where actually impurity can propagate on the ladder. So where you basically have, here, please correct me if I'm wrong, where you have an impurity which can actually propagate along a ladder. And this would be the typical thing where you get the orthogonality. But what is, we can also tunnel to actually a second chain. And at least they can probably solve this exactly, almost pretty much.
DMRG plus Bosonisation.
Yeah, and then we can answer these questions, but this is still an unsolved problem. So 2D is the exciting thing to go. Again, just doing this will then also not help you. You will have to go to actually further terms.
Is a simple way to understand why these X-ray absorption edges are signatures of orthogonality? The reason I mention this is that, for instance, in inner shell absorptions in atoms, when holes are created, you also see these sort of edges.
This is probably, okay, these edges, so I'm honestly not familiar with this part of the atomic physics, but in principle, if you look really closely onto the spectra, you would see actually still single resolved lines which, however, have an envelope, which is an edge. In typically, if you, let's say, send an X-ray on the huge atom inside the core shell, the problem is so what we're talking about is, let's suppose we have a big atom, we have the one, yeah, so we have the 1s shell. Yeah, that's much better. We have the 1s shell, then let's say 2s, 2p, and so on. We fill them all up with electrons, and more here. And then we send an X-ray in and shoot this electron to a higher state. What can happen then is, however, that in the final state, it has also contributions from one electron is going from here to here, but then this electron goes to this level here. You have, let's say, a little hyperfine split in here. Some electrons go to actually new arrangements here because it freed up energies. And in the spectrum, you will see that it's one fundamental excitation where you just take the electron from here to here and don't disturb the Fermi sea, but then you can still disturb the Fermi sea with the low energy excitations, which also gives you an edge in the spectrum. You know, in some sense, the metal, the huge chunk of metal, just has many more possible excitations which you can do. But if you have a large atom with a lot of electrons, like 20 or so, you will already see the edges. So for instance, in experiments by Seelen Jochen in cold atoms, he can do the following: a little, actually a very tiny trap where he fills in just about, let's say, 10 fermions. And in this harmonic oscillator, he can put one impurity and do a absorption spectroscopy. And there he sees, even though he only has 10 particles already, he could see the signatures of these edges. So you don't need that many particles in the end to actually create this edge spectrum.
Right, so the remark is that for the edge itself, there are two effects which are in competition.
The emission and the
the effect, which is the attraction or repulsion between the hole and the electrons. And then you have the orthogonality catastrophe. And they can either help each other or fight each other. The orthogonality is just for the Green's function of the impurity. So it's
it is also then the Fermi exactly. Yeah.
So is it fair to say that this clear signature of orthogonality requires something more than just seeing these edges?
It requires to measure the Green's function of the
Impurity. Yeah, and for that you have to address, of course, the single core excitation. And actually their cold atoms help really, because they can address just a single impurity. You know, you hit this impurity and it's not part of the Fermi itself. So that is actually a big issue with the methods to get this signature out. But we can insert just some different impurity and just address this impurity. And therefore doesn't get these competing effects also. But that's very much in the details in the end of explaining this vectors.
So, if there are no other questions, it's time to relax. For some of us to go to bed. And we'll see you tomorrow morning for breakfast. So, thank you very much.
So let me actually continue where we kind of stopped yesterday night. And we were discussing the problem of so-called Fermi polons, single impurities immersed in the gas of fermions. This might be, for instance, in volatics potassium atom in the lithium-6 Fermi gas, or if you think about the semiconductor, it might be, for instance, an exciton in the gas of electrons. Can also be, as we discussed, could be also ions in helium-3, for instance, and there are more examples of that sort. So what I want to talk about now is how it could be extracted. So we did a variational answers for the Fermi polons. We tried to extract some of the properties, or we wrote down the variational equations. And in this lecture, I want to look into the question: can we extract now the boson energy from what we have? That's kind of an obvious thing. But can we also extract now the effective mass of the impurity which gets stressed by a cloud of fermions? And can we also extract the excitation spectrum? And actually, how do we realize this in experiments and also measure these properties? So coming back to the lecture of Immanuel, he actually might make the point that we have to somehow characterize the interaction strength in the system. So we want to compare the interaction energy versus, for instance, the kinetic energy. We want to express things in dimensionless quantities. And in this case, we can consider, for instance, the kinetic energy of a Fermi gas is basically given by the Fermi energy of the system. And we can compare here, in this case, then the Fermi momentum, which is related to Fermi energy by kf squared divided by twice the mass. But kf is also related to the interparticle distance between two fermions in the gas, the average interparticle distance. And we want to compare this interparticle distance to the scattering length between the fermions and the impurity. You will remember that the scattering wave function, which was outside of the potential, got shifted towards the potential by a amount which was the scattering length. So we want to compare how much our wave functions shifted with respect to actually how far are fermions on average from each other. And this then gives us this dimensionless interaction parameter. It's actually convenient to plot things in terms of 1 over kf times a, so it's in the denominator. so that when the dimensionless interaction parameter becomes 0, then we actually have infinite scattering length. It's just very hard to plot infinite on the plot, and I will plot infinite, so it's just a 1 over infinity, which is 0. Okay, so we want to analyze this equation which we got, which was now not written, handwritten, we cannot read it, but actually notation version, where we had the variation energy, and we calculated by the variation principle with respect to the wave function an equation where we have to self-consistently determine the energy of the particle. The nice thing is this can be evaluated analytically. It's a rather nasty expression, but we can do it. So if you want to extract the energy of the polaron, what we have to do is when we have to solve this equation. We do this at momentum equals 0, and then we ask which energy do we get out. And if we plot now here 1 over KFA of our interaction parameter, we have very weak attraction here on the left side. And what I plot here is the polaron energy in units of the Fermi energy. And one sees one has a very tiny energy getting out of the system at weak attraction. But that makes sense. The impurities in the system, it just pulls fermions toward it, but really weak. And then as we increase the interaction strength and go over here, at some point there's a bound state developing in the spectrum. This is actually spectrum equals 0. And if you actually carry on to very strong attraction over here, the polaron energy keeps on increasing. Now we can ask how far we actually got with our extremely simple variational ansatz, which we can solve on basically 4 pages. One gets this energy at infinite scattering length, 0.6 times the Fermi energy. It's actually rather impressive in some sense how much energy a single impurity can pull out at this interaction strength, even in the absence of a bound state in the system out of the Fermi sea. And then we can compare this actually to different results using different methods. And for instance, here's a diagrammatic Monte Carlo result from Prokofiev and Svistinov. What they basically do is, see this really, they have all these they resum the diagrammatic series, not only in the particle channel like I thought, but in all different channels which are there. Okay, they do this to 10th loop order, but they do this and get actually this energy. And it's not so bad, we got it right by 2% in our answers. We can compare it also to multiple particle excitations, going further basically in this Shelly ansatz or the Suarez ansatz. We can compare to actually quantum Monte Carlo or also the experiment first performed by Martin Sverlak. And that's actually pretty good. Alright, so the next quantity we want to talk about maybe is, okay, how would actually the mass change of this impurity, this was like the raindrop basically falling from the sky because it got too heavy. So how heavy does the Fermi polaron become? We then take the same equation. This time we have to evaluate the final momentum because we're interested in what is the energy of the polaron as function of momentum, and then we want to get the solution and fit basically a p-squared over twice the mass dispersion ratio to it, but it's not the bare mass of the impurity, but some m star effective mass. We can put this again on the computer, solve this consistently or graphically. And what I show here is now for a rather weak interaction strength, 1 over kf is -5, very weak attraction. What I show here in blue below this red curve, I show what one gets out from this solution. Here's momentum versus the energy. You see a nice p-squared over twice the mass dispersion relation. And we can compare this to p-squared over twice the real mass of the impurity, and these two curves actually called insight, which just shows you that the effective mass of this polaron is just really not very much different, but this is very weak attraction. So the impurity pulls only a few fermions towards it actually, like a percent or so, a density increase, and that doesn't change much the effective mass. All right, then we can go to the larger attraction. We see a little bit, I mean, what one definitely sees is a shift from 0 downwards, that's the boson energy shift. And we see a very slight shift of the dispersion relation, so we get a small increase in the effective mass. And we can keep on going towards, let's say, unitarity, infinite scattering length, and there we see actually a difference that it's about 20% mass increase of this impurity in Fermi gas. All right, we mentioned 3 quantities last lecture. This was the energy, the effective mass, and the quasi-particle weight. The quasi-particle weight of the impurity tells us how similar is actually our boron to its non-interacting state. How much is actually left of its nature, this true particle nature, or this bare particle nature. And this we can extract from this variational parameter which we extracted, alpha p, and the quasi-particle weight is just given by the square of the overlap. Again, I've got here 1 over kFa versus the result which we get. And on this time unitarities here, actually still 80% is left of the bare impurity nature inside this boron. So it's actually very well defined composite, a very well defined quasi-particle. We had a longer discussion than yesterday. What happens when the impurity in the Fermi gas would get infinite mass, and where we argued that it's really cheap to make particle-hole excitations. And this would actually bring the Z factor for all interaction strength the whole way down to 0. And this would even happen for infinitely weak attraction, which makes it really a catastrophe because normally we think for infinitely weak attraction can do perturbation theory. But perturbation theory would mean that the prefactor is close to 1, and that fails. And that's really showing how problematic basically infinite mass impurities are. Alright, we can compare this also to more advanced approaches like the self-consistent letter resummation, which one can do, for instance, in the framework of a functional minimization group approach. And here one doesn't see that much difference actually. So we get, even with our answers again, this quasi-particle weight rather well reproduced. Good. Now the question is, okay, these are the properties, okay, this is all theory. Is there actually a way also to see this in experiments? Okay, the question is how can we measure the effective mass? Okay, if you would have a semiconductor or so, and an electron traveling in the semiconductor, the electron would travel through the semiconductors and interact with phonons. If you want to measure its effective mass, you want maybe to put a force onto the semiconductor and move the electrons and look at the response. How do we do this normally? We have to put an electric field on this semiconductor and just pull the electrons through. It's not so easy to do in cold atoms. Although we can have potentials, let's say, which would have a gradient, but what is much more simple, we could have a harmonic trap in which we collect blue fermions, and then we could put our impurity atoms in, let's say, a second harmonic oscillator confinement, which is actually put to the side of this harmonic confinement here, and then remove the trap for the fermion, and let's start to oscillate. And then one could actually see, for instance, dampening, and one could also try to extract from the renormalized oscillations which a massless particle would have. This was done so far only actually in experiments with impurities in the Bose gas. There are some experiments by Christophe Salomon who did similar things for fermions, but those were not completely conclusive so far. Then we have further methods. We can use interferometry. This is a question about, can we watch actually the wave function of the many-body system in real time, how it actually pulls fermions toward it and changes its wave function. So basically what we want to really study there is the time evolution of the full many-body wave function psi of t, which would be given by time evolution with the Hamiltonian, which includes now 0, and this would be initially a fermion, which is at some momentum p, an impurity at momentum p, and a Fermi C just in its normal ground state. And then you do the time evolution, you ask how is psi of t developing in time, and how does it compare actually to psi time equals 0. And you might want to ask, how is this developing over time, a very long time? This would go to something like z times the impurity in momentum p plus the Fermi C, and then comes all these corrections which we discussed yesterday. So at long times we probably approach the quasi-particle rate. This we can do in cold atom experiments. It's something which is really hard to do in solid state systems. You take an impurity which has two hyperfine states, and we put the impurity time t equals 0 just in a superposition state of one hyperfine state where it does not interact with the fermions, and in one state where it interacts with the fermions. So we kind of created this, it's not a cat state really, but it's a state where actually the system is a superposition of seeing an impurity and not seeing an impurity. And then actually by time evolving the system, when the impurity is in the down state, actually nothing happens to the Fermi C. If it's in the up state, the impurity, something happens to the Fermi C, and we can actually watch then in real time how actually this psi of t changes in time and how does it compare to the wave function at the 0. And one can then look, for instance, what happens at very long times to this velocity. Alright, there are different things we can do. We can use, let's call it, watch for changes in the medium. That's something, for instance, what we could do with single-site resolved microscopes. Let's suppose we have an impurity in a lattice system, and then we could actually just watch what happens to the atoms surrounding the impurities. Are there some correlations we can see just because an impurity is there? A different way of seeing changes in the environment is, for instance, watching for transport properties in the medium. So, for instance, if we have a pure spin-up Fermi C, and then suddenly we throw in an impurity which actually allows that when spin up at the top of the impurity, they can change their spin. Then what we suddenly would see in the medium, that we flip spins in the medium. And this one can actually also do cold atoms using Ramsey schemes. And finally, this is what I want to talk about now briefly, is we can also do spectroscopy. And how would this work? We take our Fermi C, and we throw an impurity into the Fermi C. Let's say this is a lithium 6 Fermi C, a potassium atom. Potassium atom has a lot of hyperfine states. And using phase resonances, we can use two hyperfine states where one hyperfine state is not interacting with the environment, and one state is actually interacting with the environment. So if you prepare the system experimentally first in a hyperfine state where it's not interacting with the environment, it's just described by the non-interacting Hamiltonian, and its ground state is just given by the impurity, it's a momentum p, and the Fermi C. And the impurity is in spin state 1. But now we can use a RF pulse on the system and drive actually the system, or try to drive it into the state 2. And this is then given by time-dependent perturbation, which basically changes the hyperfine state from the impurities from state 1 to state 2. Alright, how do we calculate this? In the most simple fashion as theorists. The transmission rate, or the transfer rate from state 1 to 2, there's a famous formula for doing these things.
Fermi-Golden rule.
Exactly, Fermi-Golden rule. So this is what we will calculate. This is valid as a linear response. And so what it basically measures is, this is the absorption at a certain frequency. And what we have to do is we prepare the system with some initial state. We apply some time-dependent perturbation. In this case, this is our perturbating operator. We have to sum over all possible final states of the Hamiltonian in the final state of the system. And then we will always pick up a delta function when we hit exactly the right energy of a final state. So how would the spectrum look like? This is now tilted around. Here is the absorption versus frequency. Okay, let's scan this formula. If the frequency hits one of the final states, we get a delta p. We calculated one specific state, and this was the pull-on state. If you hit the boson state, this is an approximate, if you were really good, we would have calculated the exact wave function. This would have been an eigenstate of h, and you would pick up a delta function when we hit exactly this energy with a weight or height which is given by the z vector. But there are, of course, many more possible final states of this
Can I ask you a question? Can I ask?
Sure.
So how does the width of this resonance compare to the T2 dephasing rate that you get, for example, with your Ramsey method? Because in this width, you not only have the dephasing, you also have the lifetime somehow, no? Or
Sure. So what I considered here, so that's kind of a tricky question.
Okay.
So if you're at zero temperature and you have a well-defined Gaussian particle at zero momentum, it doesn't have a lifetime. It's infinite lifetime, and it would be a delta function. There would be no width. And that's kind of connected to that in the long time evolution, this thing here would go just to z. And if you take the Fourier transform of a constant, that's a delta function of height z. However, if you have final temperature, for instance, or the T2 time, basically, which you get, it gives you the width of the peak, which would be 1 over T2 time is the width in the spectrum. So what Emmanuel is referring to, for instance, if you have a thermal gas, or if you have some intrinsic lifetime of the particle, then what can happen is the following. That the particle or the many-body system starts to actually time evolve, and if you had zero temperature and you would have a well-defined boson, in the beginning, well, it's a Fermi not stressed with anything, impurity not stressed with anything, and of course at t equals 0, this thing is just psi of t equals 0, so we start at 1, and then this object starts to decay. And it would go to the z factor if you have a well-defined Gaussian particle. If you are at a finite temperature, for instance, or if you have decay, if I plot this here on the log scale, then you would get an exponential decay, and this is the T2 time, which actually Emmanuel is mentioning. And this T2 time would actually give a broadening of this peak here, which just scales like how fast this exponential decay is. All right. So we can calculate this absorption spectrum using Fermi's golden rule. And this time, I'm sorry, I do something nasty. Here's a minus sign. So before weak attraction was here, now weak attraction is over here. It's just because experimentalists will like to plot it this way. So we have weak attraction here. We already got in the ground state the delta peak when we hit the boron energy. And this is the so-called attractive boron, which becomes more and more deeply bound as we go to stronger and stronger interactions. Now, what one, however, finds as well is when we go to stronger interactions, we find in the ground state, but we also find actually an eigenstate of the Hamiltonian at finite frequencies. And this is actually given by the so-called, or this is the coherent excitation of the system, where actually the impurity likes to push away the fermions. It's an excited state of the system. It has a finite lifetime and therefore a finite broadening. It's called the repulsive boron. And if we would have done an additional calculation, we would actually find that the Hamiltonian supports also states which are the molecular state. So here, the impurity decides actually to catch one of the fermions out of the Fermi sea with a molecule, and then you have basically a system where a single molecule, so in this case, we would have our impurity, we would have some fermions, and so far we consider kind of the situation where the impurity is kind of free and it moves through the system and maybe hops in quotation marks from fermion to fermion. It can, however, also decide, come on, attraction is so good, let's take one of the fermions, let's build a bound state and then travel as a bound state through the system. So kind of it's a molaron instead of a boron. Maybe that would be the right word. If we would like to calculate this, well, this was not inside our wave function. So we should choose a different wave function. Let's call the wave function M. And how do molecular wave functions look like? Well, in the center of mass frame, this would be in impurity at momentum minus k, a fermion at momentum k2 to momentum 0, and they would have some envelope wave function alpha of k. and this acts on the Fermi sea. And then you can ask, this is a molecular state, it's the exact molecular state if there's no Fermi sea, and then it's getting modified to Pauli blocking. It's actually similar to an answer which you have also in DCS theory. And if you do this, you would find that there's actually transition at some point from a polar to a molecular state. However, that we didn't do in this lecture now. Good. Now, Rudi Grimm actually performed this experiment a couple of years ago. What he did is the following. So he prepared a large lithium-6 Fermi gas, and then, so it has this gigantic is maybe too much, but he has a harmonic trap in which he fills in a lot of lithium-6 fermions, and then he uses the state-selective potential-based rod, a second potential, to trap in the center of the trap a very small fraction of potassium atoms. So it's a density, so if you compare here the density of the potassium divided by the density of the lithium, he had around 10%. So it's a small, it's not that small, but at least it is only about every, I don't know, 5 or 6 interparticle spacings of the lithium atom the next impurity comes. It's not perfect impurity physics, but okay, it's as good as you could get. So what he does then is, he starts exactly from the scheme which we want to do here. It's called injection spectrum, or spectroscopy, because we inject an impurity into the system basically. So we start with a potassium atom in a hyperfine state, we drive an RF into an interacting hyperfine state, and we watch how different, or how does the lithium-6 Fermi behave, and we want to see the spectroscopically. And this is what you observed, and it looks actually very similar to what we just got from our theory calculation. The same stuff was actually done then also by Michael Köhl in Cambridge, where he actually used a two-dimensional system. Basically, he had retroreflected laser beams, make pancakes out of light, split in fermions in there, and the same physics in 2 dimensions. And this is actually so this line here is the one which we calculated with our Chevy ansatz, and it fits actually pretty nicely on where the experiment finds the energy of the photon. Well, no wonder we just saw that we are right up to 2%, we have to diagonally one particle. All right. Now I cheated you a little bit though, because I suddenly threw actually excited states of the Hamiltonian, and we did variation principle, so we minimized energy and got just the lowest state of the system. So how do we find actually all these excited states of this Hamiltonian, and how do we find their eigenenergies? We did variation principle just for the ground state. And so the question is, how could we get there when we just work with variational wave function of this type? Maybe this actually you can also apply to different types of variational wave functions, what I'm talking about now. So we definitely have the initial state of the system in the Fermi's convoluted, sorry, this should be precise 0, which is the impurity in the Fermi sea. In the final state, the impurity definitely changed its hyperfine state, otherwise nothing would happen. And then we had this type of Chevy-Surlis ansatz. But now we can ask, well, this can not only describe ground state properties, but also excited states. They are approximate as well, but okay, at least one could build excited states out of this. And so let's just plug in those wave functions in the Fermi's convolution and see what we get out. So we have psi 0, we start with this guy. Then we have our laser operator, or the RF operator, which takes psi 1, kills it, and makes out of it a psi 2. Then we have to build the overlap with the final state. Psi 1 became psi 2. Well, this actually works with this guy over here, but it only works with this guy if it's exactly at the same momentum. So this term cannot contribute to this overlap because that's at a different momentum. So actually what we will get is that this object here just becomes this alpha p squared. And again, this is just what we called before the quasi-particle wave. That's the reason why the height of the peaks in absorption is just the quasi-particle wave. Okay, I can't even tell you anything how to calculate this. And And we only had so far the ground state, just one of the states out of the whole manifold of states which you can build up with such a wave function. So one thing helps actually to get a little bit insight where these states are, is if you look at the minimization equations which you wrote down yesterday. So we had two equations which we then solved. One equation you got from from the variation with respect to this alpha p star, so the first part of the ansatz, and then we had the second equation from the second variation. And if you look at this, this is basically a matrix structure which multiplies a vector which has inside this alpha p, so it should be alpha p, and then the alpha kq, and I could build up a huge vector with this. And then it just multiply a matrix times this vector. Here's an alpha, 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 equal to e times this vector, but that's just the solution to get actually the eigenstates, or the eigenimages of the system. So we get a linear equation. So we have an effective Hamiltonian multiplying some vector, and we could basically diagonalize this thing. All right. The thing is that we get a linear equation system is actually no surprise, because then our wave function consists of two complete basis sets. Namely, one basis set is rather simple. It's just the zero particle hole excitation basis, efferency and no particle hole excitation. Then we had the second term, which was the next part, a single particle hole excitation. Let's call it KQ from now on. And what we had in front of these terms were our variational parameters, but these were completely general. So what we just built, this is a basis set, and we just try to get the optimal basis vectors basically to get the ground state, but in principle we could get every excited state. Since we have a complete basis, we actually should get a linear equation system because we have linear quantum mechanics. So basically what we did perform yesterday was actually a diagonalization in a truncated Hilbert space of zero particle and one particle hole excitations. So the question is now,